Good morning, Calculus, Mr. Florio. This is section 6.4, the logistic equation. So our goal is going to be to solve and analyze some of these differential equations and then use it to answer questions and solve applied problems. So what is the logistic differential equation? Some call it limited growth, and I'm going to send you some other videos that have more on it. But in the last section, so in section 6.2, the exponential growth model was derived from the fact that the rate of change of the variable was proportional to the value of y. So y prime was y times some constant. And then we observed that the differential equation, the rate of change is equal to some constant times y, has the general solution of y equals c e to the kt. Exponential growth is unlimited, though. But when we're describing a population, there's often some upper limit L past which growth cannot occur. The upper limit L is called the carrying capacity, which is the maximum the population y of t that can sustain or support as time t increases. So a model that is often used to describe this growth is what we call the logistic differential equation. So a couple of things here. The idea is, say there's you have a population growing, or a population gets some sort of disease, and let's just you could use COVID if you want, but we start off with a disease. There's some amount of people that start off with it. Whether it's 1, 2, 3, 4, 50. And the amount of people that get it over time increases dramatically. So one person passes it on to two. Each of those people pass it to two more. So now that 4 people have it. Each of the 4 people a day later pass it on to someone else. So now 8 people have it, 16, 32, 64. It just grows exponentially. But what happens is, I don't know, I think, let's say like there's about 7.5 billion people on the world, on the planet. You can't have more than 7.5 people get infected with it, because that's the amount of people that we're kind of holding. So this is kind of like the ceiling. And what happens is this thing grows really quickly, except at a certain point, we have millions of people infected, but they're infecting other people who are already infected, and you can't infect someone who's already infected. So there's less people to infect. And as there's less people to infect, even though we're growing fast, now those people that are going out and infecting other people, well, those other people are already infected. So now there's less people to infect, so the amount of people left is going to kind of slow down, and we're going to slowly keep infecting more and more people until we get to that carrying capacity, which is 7.5 billion. There's that many people in the world. That's how much people the world can hold. So think of like a pond that can carry, say like a pond has a carrying capacity of 1,000 fish. If you dump 2,000 fish into that pond, so if we start by more than our carrying capacity, what happens to the population? Well, there's not enough food for them, and they're going to die really quickly. They're going to hit that carrying capacity, and then they'll stay at that 1,000 fish for a while. But 1,000 of the fish are going to die, and there's ways to account for people being born, but people dying, and you got to kind of, if you wanted to be more exact, you could take that into account. But what we're going to focus on is this type of model right here, when the initial population is under the carrying capacity, and how do we get up to that carrying capacity? We won't really see this bottom one too much. Okay, so a couple of things. This we have a differential equation that can represent this. Now, the rate of change of I'm going to call it, instead of y, I'm going to use p for population. The rate of change of the population over time is going to be, well, we have the population, and we know that the population is proportional to the rate of change is proportional to the population. So whatever the population is, a certain amount of people are being infected by a disease, or the population is growing by a certain constant over time. So we'll call that constant K. So if the rate of change is, every day 4 more people are being infected, or the population is growing by 4, then you multiply the population by 4 every day. So that's the constant. Now, what happens, though, is that it's limited. Eventually, you start running into people who are already infected, and you can't infect them again. So you can only infect the fraction of the population that's still susceptible. So the amount of people that are infected is the amount of people that are in population that are infected over the total population. That's how many people are infected. So that's a fraction of the population. And so say that's 20% of the people are infected, that means 1 minus 20% or 80% of the people are susceptible to being infected. So this is the fraction of the population still susceptible. This right here is the population. And this is our growth constant. Okay. And quickly, this L, by the way, is what we call the carrying capacity. Okay. So what's happening here? A couple of things. If my population is less than the carrying capacity, so if I have something like this, where the amount of people that start off with the disease is under the carrying capacity, so if the population is less than the carrying capacity, which it normally is, then we'll see growth. Then the rate of change is positive. The function is going to be increasing. So as you can see, this function is increasing the whole way. If the population is greater than the carrying capacity, so if you put more in than the population can handle, maybe there's not enough food or resources for that many people to survive, then the rate of change of the population over time is going to be negative. The population will be decreasing. Okay. So we're going to stick to problems like this where the population is less than the carrying capacity, and we're going to grow to that carrying capacity. All right. So how can we solve this differential equation? And instead of P for population, they're using Y, which is fine. To solve this, I'm going to send you a video that kind of walks you through it, but I'm not going to take the time to solve it. This is how the book solves it. Everything in here is doable, except I don't think in pre-calc you've done something called partial fractions. And if you took pre-calc honors, maybe. It's a pretty tricky thing, but the idea is breaking up one fraction into two fractions with two different denominators. So it's kind of working backwards, but again, there'll be a video if you want to see it. You just kind of solve a small system to get it, but I'm not going to take time going over that. But this is what's important. This is the equation. This is the logistic equation. Based on, we can come up with this, the differential equation that models this logistic growth, this limited growth. When we solve that differential equation, we can get an equation that models the population, and this is what it is. Again, L is the carrying capacity. B is just some constant. And K, I believe, is what we call the growth factor. Growth or decay factor. T is obviously time. For the application problems, but you can think of T as just like your independent variable. And Y is your dependent variable. And a lot of times it'll model population. Okay. So here's an example for the given logistic differential equation. Given logistic differential equation. We need to find the initial conditions, find and verify the upper limit, and determine the points of inflection. So first, the initial condition. We want to find out what's the population when the time is 0. So when t equals 0, what's the population? Simple enough. The population y is equal to 4 over 1 plus 2e to the negative 3 times 0. So when t equals 0, what is the population, or what is y? call it y of 0. And what do we got? Well, let's see. That's 4 on top. On the bottom, I have 1 plus. Well, e to the 0 is 1. 2 times 1 is 2. So that's going to be 4 over 3. So the initial population is 4/3. It's not a whole number. If you were doing like a human population, obviously you'd have something like a whole number. But in this particular model, with the numbers kind of what they are, the initial population is 4/3. Let's go to part B. Find and verify the upper limit. So the upper limit is the carrying capacity, and that's this number right up here. So L in this case is 4. We want to find it and verify that that's true. So the idea is, as time goes on, as time gets really, really big, as we go deep, deep into the future, this model should approach 4, or whatever the carrying capacity is, which is what we saw right here, right? As time goes on, we should approach this carrying capacity, which is whatever L is. So that's L. Okay, so does that really happen? Well, let's find out. What's the limit as we go deep into the future, as time approaches infinity, as we go way, way into the future, so to speak, of the population, 2e to the negative 3t. Well, let's see. The limit as t approaches infinity of 4, and then the bottom, the limit as time approaches infinity of 1 plus 2e to the negative 3t. You don't have to do all this limit notation, but just think, as t gets infinitely big, the numerator is 4. It's not being multiplied by anything that has to do with t, so that's just going to stay 4. This 1 is going to stay the same, but as t gets really, really big, it's being multiplied by a negative number. So this is like e to some, negative infinity. And think e to negative infinity, think of that as being 1 over e to the positive infinity. And when you have 1 divided by a big number, you get a really small number. And if that number is infinity, then we're really just approaching 0. So this thing right here is approaching 0. And 0 times 2 is 0. 1 plus 0 is 1. 4 divided by 1 is 4. And it checks out that as we go to kind of infinite time, as time goes deep, deep into the future, the carrying up capacity does approach 4. All right. And then the last one is C, determine the point of inflection. So the point of inflection is also the point where the growth rate is the greatest. Without doing much calculus, this thing is going to be the greatest. The point of inflection is right here, which is where it's increasing the most. The inflection point is always going to be whatever the upper limit is divided by 2. So it's going to be halfway. So if the population was 1,000, then the inflection point would be at 500. If the carrying capacity is 7.5, it's going to be half of 7.5. It's always going to be halfway. The book goes into detail about finding that, but we don't need to do that. So determine the point of inflection. So L over 2, the carrying capacity is 4. So 2. So the point of inflection occurs at the y value 2. To find the time value, at what time does it get to be 2? We just have to solve this differential equation for that. So the point of inflection is at y equals 2. So if I replace the y with 2, we just need to solve this equation for t. So what I'm going to do is multiply both sides by the denominator. Uh, 1 plus 2 e to the negative 3t. And then if I divide both sides by 2, the 2's cancel out, and we're left with, on the left-hand side, 1 plus 2 e to the negative 3t. That canceled out, so 4 over 2, that just leaves me with 2. Subtract 1 on both sides. 2 minus 1 is 1. I could go about this I'm going to go about this by 2 different ways. The first way is I'm going to multiply both sides by e to the positive 3t. So 3t minus 3t is 0, and e to the 0 is 1, so those will go away, and I'm just left with 2. Equals 1 times e to the 3t is e to the 3t. Take the natural log of both sides. The natural log of 2 undoes the e, so I just get 3t. Divide both sides by 3. And the natural log of 2 divided by 3 is the time it takes to get to that inflection point of 2. So we can do the natural log of 2. Oh. Shoot. Natural log of 2 divided by 3. So it takes this many units of time, 0.231. Just zooming back into where I was here for a second. A way I could have handled this when I had the 2e to the negative 3t equals 1, I could have just divided both sides by 2. And then got e to the negative 3t equals 1/2. And then take the natural log of both sides, and then negative 3t equals the natural log of 1/2. And then divide both sides by negative 3. And the natural log of 1/2 divided by negative 3. These are actually equivalent. Believe it or not, and I can show you right here. If I did the natural log of 1/2 divided by negative 3, I'll still get that same 0.231. So it's the same. So either one of those solving, you would have got the same number. And that was it. Okay, so I do want to look at this on a graph real quick, but so at 0.231 comma 2 is where the point of inflection is. And at 0.231, the exact way to write that would be 1/3 natural log of 2. Looking at this graph real quick, let's kind of see what happens. So here I typed in the equation, y equals the carrying capacity over 1 plus some constant e to the negative kt. And if I make that constant, if the carrying capacity is 4, I'm going to bring this up to 4. So that's kind of how it maxes out at. That constant b, they got to be positive numbers, so you're not going to see anything weird like that. They said b was 2. And k was 3. So this is a graph of that model, and that is that logistic growth where we started off at 4/3. That was like our initial population. So 1.33 is 4 1/3, or 1 1/3. And we said the point of inflection was at about 0.2. So we're at the height has got to be half of 4, which is 2. This is where the point of inflection is. And I mean, I'm at not exactly 2, but 0.24 is pretty much what we had. Right here, 0.231. So you can even play, like how does changing k affect it? The higher your constant is, the faster your graph is going to slope up. It's going to have a quicker rate of change. How does b affect it? B, it looks like it's like pushing it over to the right a little bit. And the carrying capacity tells you how high and low you can go. That's how much your population can handle. All right. So last example here. Yep. All right. See if we can put it all together in an application problem. Solving a logistic equation. A state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commission believes the environment can support no more than 4,000 elk. The growth rate of the elk population P is given by this differential equation. write a model for the elk population in terms of T, use that model to estimate what the population will be in 15 years, and find the limit as T goes to infinity. All right, sounds pretty tough. Let's just break it down to a couple things. The state game commissioner releases 40 elk into a game refuge. So their initial population at time 0 is 40. So that's like the initial condition. After 5 years, the elk population goes to 104. So in 5 years, the population is 104. So think when T equals 0, the population is 40. When T equals 5, the population is 104. Right? So these are time, comma, population. That's what's being related here. The environment can support no more than 4,000 elk. So 4,000 is the carry capacity. And we want to write a model for this. So the model for our population, we solve this differential equation, is L over 1 plus B e to the negative KT. And we need to find out what LB and K are, and I know L is 4,000. We want to find out what the population is. Let me use these points here. At time 0, the population is 40. So e to the 0 is 1. So 40 equals 4,000 over 1 plus b times 1 is b. What I'm going to do is multiply both sides by 1 plus b and divide both sides by 40. So if I multiply both sides by 1 plus b, that goes away, and I have a 1 plus b over here. And if I divide both sides by 40, that 40 will go away. And 40,000 divided by 40 is, 4,000 divided by 40 is 400 by 4. That's going to be 10, I believe. Or is that 100? Yeah. Okay. So if 1 plus b equals 100, then b has to be 99. Okay. So we have b now. We have L. I need to find K. And I'm going to use the second point here to find K. So that's part of it. To find K, let's do the population is 104. And that's when, so the population is 1 plus b e to the negative, well, when time is 5. Let's see if we can solve this for K. So I'm going to do the same thing. I'm going to multiply both sides by the denominator, which is 1 plus 99 e to the negative 5k, and then divide both sides by the 104. So 4,000 divided by 104. It's not that nice of a number. Let's see if we can keep into a fraction now. 4,000 divided by 104. Let's put that into a simplified fraction. That's 500 over 13. Subtract 1 on both sides. So if I subtract 1, that's the same thing as subtracting 13 over 13. And the 500 13ths minus 13 13ths is 500 minus 13 is 47. And then divide both sides by 99. 13 times 9. So if I divide by the 99 will be in the denominator with the 13. And 13 times 99 is 1287. Can I simplify that? 47 divided by 1287. Nope, Doesn't simplify. And you could take the natural log of both sides now. I can bring the e to the -5 to the other side to make it e to the +5. It doesn't matter. I guess we'll look at maybe both ways. If I want to bring the e to the other side, I'd multiply both sides by e to the 5k. These ones would cancel out, and I would have an e to the 5k over here. To get this on the other side, I'd just multiply both sides by the reciprocal, which is 1287 over 487. Just take the natural log of both sides. So the natural log of 1287 over 487 equals 5k. And if I want to get the 5 by itself, just multiply both sides by 1/5 or divide both sides by 5, and that'll be my answer. Alternatively, I could have just done that right here. If I took the natural log of both sides, I'd have -5k equals the natural log of 47 over 1287. And then if I just divided both sides by -5 here, so times -1/5. These are going to give me the same answer, whether I did this or this. And let's see what that answer is. We have the natural log of 1287 by 487. And we got to divide that whole thing by 5. And that's going to give me about 0.194. Okay, so that's the constant. That's that growth constant k. So here we are. So now I can finally finish part A. The model for my population is my carrying capacity over 1 plus b, which I know is 99, e to the -k, which is 0.194 t. So that's part A. Part B we're going to skip. We're not going to do things with slope fields. We'll look at part C. Use the model to estimate the population when t equals 15. So we're just going to plug 15 in here and we'll be done. So the population model is 4,000 over 1 plus 99 e to the -kt, and t is going to be 15. Let's pop that in, see what we get. 4,000 divided by everything in the denominator is 1 plus 99. Oh, shoot. 4,000 divided by 1 plus 99. E to the -0.194 times t, which is 15 years. Close that parenthesis. And it looks like in 15 years, the population will be about 626. And so that's C. This was part A. And D. So if I want to find the limit as time goes to infinity, so what's going to happen in the future, it's just going to hit that carrying capacity of 4,000. As t goes into infinity, this is just going to approach, let's use a different color. This is just going to approach 4,000. As t gets really big, it's going to be 1 plus 99 times. As t goes to infinity, e to the -infinity is going to approach 0. So 99 times 0 is 0. So it's going to be 4,000 over 1, which is 4,000, which checks out with our carrying capacity. So that's what happens as time goes on. Anyways, so your homework is going to be applications of this. Sometimes you'll be going from the differential equation to the actual equation, going from the actual equation to the differential equation. just knowing what your variables are, plugging them in. Any question on the homework, just feel free to give me an email, give me a shout. Anyways, that's it. I'll post some more videos too in regards to the logistic equation. All right.